Section 3.6 is hyperbolic functions. So these are very similar to exponential functions. You'll see that all of the, or most of the definitions for these functions involve the natural e to the x exponential function. So they're actually kind of a nice function to deal with, even though it is one more layer of stuff that we have to know in the course. They are very useful functions in applications, and perhaps we'll see some of that in later calculus courses. But they're pretty nice in terms of calculus that's involved with them. So here's the definition of hyperbolic functions. So note that we use this convention of sine with an h. So that's hyperbolic sine, cosine with an h, hyperbolic cosine, hyperbolic tangent, and so on. So just a subtle difference in the notation. Now, this is the definition of these functions. Hyperbolic sine of x is e to the x minus e to the negative x divided by 2. Okay, and cosine, hyperbolic cosine is very similar with a plus sign between those two exponential functions. Then we define hyperbolic tangent of x as hyperbolic sine of x over hyperbolic cosine of x. Similarly, down the line for hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. So that's pretty easy to define. And we have a nice list of identities that will be helpful from time to time. We're actually going to start by proving some identities, but namely this one, and I believe another one or two on this page. So nonetheless, these are handy to keep around. Notice the difference. This is not quite the Pythagorean identity. It's not an analog of it exactly. Or maybe it is an analog, just with a minus sign in the middle. So there's a difference there. And at times this sum formula might be helpful for us. And this is an even and odd property of hyperbolic sine and hyperbolic cosine. And then lastly, sort of another kind of a pseudo analog of the Pythagorean theorem. So let's have a look at how we would prove a couple of these identities in case we ever need them or need to build our own identities. And it looks like the following, right? Back in trigonometry, you learned how to prove an identity. In other words, that this function equals that. And you'd start with one side. In this case, I'll start with the left-hand side. And you try to arrive at the right-hand side, right? Just by a series of legal moves or manipulations and substitutions. So hyperbolic sine of negative x. Well, remember from the definition of hyperbolic sine of x that this is what we have here. This will be e to the negative x, because we have a negative x there, minus e to the negative x. And we see that reflected on the next page here, right? So here we are. We've plugged that into, well, the definition of hyperbolic sine. And we have the following. And now we just need to sort of resolve these minus signs in the exponent. And this gives me an e to the negative x minus e to the x. This is, of course, a positive x here. Now everything's over 2. We haven't moved any of that around yet. And what I realize now is if I swap the order and then put a minus sign out front, so I factor a minus sign out of here, I get e to the x minus e to the negative x. There's a minus sign out here. Of course, if you need to see that the step is correct, take this minus sign and distribute it through the numerator again, and you'll see that you arrive at this expression, again with the terms just rearranged. This is actually negative. It's e to the x minus e to the negative x over 2. And if you look on the previous page, you see that that's actually hyperbolic sine of x. And this minus sign just kind of comes along for the ride. So we've now proved that hyperbolic sine of negative x is equal to negative hyperbolic sine of x. And that's just based on writing out the definition of hyperbolic sine here and working on these exponential functions, as we know how, since we already know how to deal with those, and then seeing that we arrive at this value here. So similarly, let's look at, we've got another identity here. Hyperbolic cosine x minus hyperbolic sine x is equal to e to the negative x. Maybe that's a useful identity somewhere down the way. So let's have at it. Note that there are tons of different identities involving hyperbolic functions, and they're kind of fun to work with, to prove or to derive if, once we get the hang of it. It's actually a little bit easier than trig functions, I think. Well, nonetheless, so let's start with the left-hand side again. We don't always have to start with the left, but I think it's easier to start with the side with more complication, and we can reduce to the side with less complication. So cosine, hyperbolic cosine x minus hyperbolic sine x. So here's hyperbolic cosine x minus hyperbolic sine x. Again, this is just from the definition of each of these functions. Oftentimes when you prove these identities, you'll go back to these definitions. And well, here I'm going to factor out 1/2 from each of these and write this all as one group. So here's 1/2, and then I'm going to have e to the x minus e to the x. So that's those terms. And then I've got e to the negative x minus negative e to the negative x. So e to the negative x plus e to the negative x, right? Minus minus gives me a positive there. So let's see what happens to those exponential functions. These two add to 0, and these two add to twice one of them, right? So we have 2e to the negative x. We have a 1/2 out front still, and 0 plus 2e to the negative x. So that's 1/2 times 2e to the negative x. We end up with e to the negative x. We've arrived at the right-hand side, and this identity has been proved, right? The squares here are little end of proof symbols, right? End of demonstration. Okay, so let's prove hyperbolic cosine of x plus y is equal to this sort of tangled mess, right? This is a sum identity for the hyperbolic cosine. So we have a nice hint, and really generally the way you'll think about this is like I did before. I started with the side with more complicated terms, right? If I were to start with e to the negative x to try to prove this one, I'd kind of gridlock myself. There's no terms to simplify or to cancel or simplify or manipulate. Sometimes it's easier to start with the side that's got more going on and try to arrive at the simpler side. This is just a matter of cancellations often. So here we are. We'll start with, oh, I actually didn't do a very good job of writing this down, right? I actually missed half of this. So let me write the other portion in here while we're at it. But you see what I've done? I've taken what hyperbolic cosine x times hyperbolic cosine y is, and added to it hyperbolic sine x times hyperbolic sine y, right? So here are all four of those functions, right? This is hyperbolic cosine x times hyperbolic cosine y plus hyperbolic sine x times hyperbolic sine y. Okay. Now I have a 2 and a 2 in the denominator for this side, for this multiplication here. So I'm going to get a 1/4 out of that right here. And then I've got a binomial, pair of binomials to multiply times each other. So I have e to the x times e to the y is e to the x plus y. So that's this term. Then e to the x times e to the negative y is plus e to the x minus y. And now this term, e to the negative x times e to the y plus e to the negative x plus y. And then this term, e to the negative x minus y. So we get all four of those terms there. And I do something very similar over here on hyperbolic sine side. I just have to be careful of these minus signs. Remember, when you multiply two exponential functions, you add their exponents. E to the x times e to the y is e to the x plus y, and so on down the line. Now we know that each of these is times 1/4. So I can combine this, right? So what I'll end up doing is I see that this and this term will add to be 2 times e to the x plus y. This term and this term adds to 0. This term and this term add to 0. And the last term, e to the negative x minus y plus e to the negative x minus y, that adds to be 2e to the negative x minus y. So I have 2 of these, and I have 2 of these, and there's a 1/4 on the outside. So 2 cancels with 1/4 to be 1/2 times those values. And now here's where I have to be a little bit clever about this, and I look at this and think about it, and I look at what I'm trying to arrive at. And I realize that, and maybe I even go backwards and write this down and see that it's equal to this, which matches this. But nonetheless, through this intermediate step here, I see, okay, this is e to a something, that's x plus y, and this is e to a negative version of that something, a negative x plus y as a group. In between them is a plus, and I have division by 2. So that's the hyperbolic cosine of this argument x plus y. And there I arrive at the right-hand side proving this identity. So again, remember the other alternative is to break this up, split it up as is, expand it, do simplifications here. And if you get to something like this and you're not sure, well, then start with the other side and build the bridge from the other direction, right? And try to match this to that, and then you'll have it. So, all right, next up, derivatives of hyperbolic functions. This should be easy because hyperbolic functions are defined as exponential functions with base e, right? So let's see how the derivative of hyperbolic sine of x is equal to hyperbolic cosine of x, as stated here in the table. Now, of course, I wouldn't be too often that it's not so likely that I ask students to prove this on something like an exam or a quiz, but it's not a hard proof, so it might be a pretty good problem. But most of the time, once we have these new derivatives, we'll just be able to use them for more complicated problems. So the derivative of hyperbolic sine of x is equal to the derivative of e to the x minus e to the negative x over 2, right? That's the definition of hyperbolic sine of x. Well, the 2 in the denominator comes out as a factor of 1/2 by the constant multiple rule. And then I'm taking the derivative of the numerator now. Well, the derivative of e to the x is e to the x, and the derivative of e to the negative x, well, it's e to the negative x with a minus sign times this exponent times this function. So that makes this positive. And when I look closely at this, I realize this is actually hyperbolic cosine. And now I've proved that the derivative of hyperbolic sine of x is hyperbolic cosine. So these are pretty easy. We don't have to go back to that limit of the quotient or the difference quotient situation and do all that old work we used to do. So prove that the derivative of hyperbolic tangent of x is hyperbolic secant of x squared. Well, the derivative of hyperbolic tangent of x is hyperbolic sine x over hyperbolic cosine x. Well, if I look up top, I can just use this fact. If I really wanted to, I could be thorough and prove this one. It would be very similar to how we proved that one. Nonetheless, I've got these in hand. The derivative of the numerator, hyperbolic sine x, is hyperbolic cosine x times the denominator. And then minus the derivative, minus the numerator times the derivative of the denominator. Hyperbolic cosine x's derivative is hyperbolic sine x. What I see in the numerator now is hyperbolic cosine x squared, hyperbolic sine x squared. And I have to recall that this identity, if you go to the very first page, you'll see that this is equal to 1. And again, if you don't believe that identity, that's an identity that you could prove. Write this down somewhere and prove that this numerator up top is equal to this value of 1. Start on this side and expand them as their definitions, and you'll see that this actually does work out. Anyway, we're left with 1 over hyperbolic cosine squared of x. Well, that's hyperbolic secant squared of x, and that's exactly the derivative that is being asserted here. So that's how we go about proving these identities, proving these derivatives are what they are. So now just derivatives in general with hyperbolic functions are just like any other functions, any of the other functions we've ever dealt with, right? Here, I'm asked to compute the derivative of g of x, and I have hyperbolic cosine of natural log of x. So I take the derivative of the outer function, hyperbolic cosine's derivative is hyperbolic sine of the inner function, right? And now I'm done with this term, right? Don't make mistakes with the chain rule here. I'm done with that part, but I have to multiply by the derivative of this inner function, right? So here's the derivative of that inner function as an operation here lined up for us. Well, the derivative of natural log of x is 1 over x. So I'll rearrange this. Usually rational functions precede transcendental functions as multiples. That's just a convention. So I put 1 over x times this function, and I'm done. I've just carefully executed the chain rule with a hyperbolic function derivative. Now we have hyperbolic sine of hyperbolic cosine of x. So again, another chain rule. So hyperbolic sine's derivative is hyperbolic cosine of its argument. So I'm done with this term now, and I proceed to multiply by the derivative of this function, right? The argument, derivative of the function and the argument. Well, the derivative of hyperbolic cosine of x is hyperbolic sine of x. So there we have it. We have hyperbolic sine of x times hyperbolic cosine of x. Okay, don't try to put these two things together. I saw some mistakes with this in past exams where people try to start merging together these functions. This is the hyperbolic sine of x. This is the hyperbolic cosine of the hyperbolic cosine of x. They really don't mesh together in any nice way, and leaving it as is just fine. Okay, lastly, we have to find the derivative of hyperbolic cosecant of t times 1 minus natural log of hyperbolic cosecant of t. Pretty solid mouthful. All right, anyway, so f prime of t, I need to use a product rule. This function, its derivative, times this function is my first term. That's actually my first line. The derivative of hyperbolic cosecant of t is this. You can look that up on the previous page, times this function. So here's all that. And then the other half of the product rule is plus this first function times the derivative of the second function. Well, this is the first function. The derivative of the second function is pretty complicated, right? The derivative of 1 is 0. So I automatically just have negative. Whatever natural log's derivative is, it's 1 over hyperbolic cosecant of t. So here I have the derivative of natural log, right, with its argument being hyperbolic cosecant of t. The minus sign comes from right here, 1 minus. And then times, I need a chain rule, right? I need to multiply by the derivative of hyperbolic cosecant of t, and there's where that derivative goes right here. That's what that is. Now, this is a pretty good mess, right? So what I have, though, is I have a negative times a negative, so that'll be a positive. And both of these functions actually have this multiple. And really interestingly enough, I guess I don't cancel these negatives yet. Both of these have a negative in front of them too. So what I'll do is I'll factor the two terms that are highlighted out of this expression, and I'll put all the rest of it together. Well, let me see how it looks. Here's this term, these terms, multiples factored out of the rest of the expression. So they're times the group 1 minus natural log hyperbolic cosine t, and then minus this portion, hyperbolic cosecant t times negative 1 over hyperbolic cosecant of t. Well, that cancels to negative 1, so there's that negative 1. And then this positive 1 and this negative 1 add to 0, and what we're left with is just the negative natural log of hyperbolic cosecant of t, and the minus signs will cancel. And in the end, we have this times natural log hyperbolic cosecant of t. So sure, that one's really complicated. It's kind of bad to talk through, or probably even to listen to. So, these are things better done, quietly practicing on your own. But, as we've seen time and again now, we've learned a new set of derivatives, right? A new list of functions with derivatives that we can work with. And we see how we might come up with those derivatives if we were to forget them, or if we were to be asked to prove them. But more importantly, what we know how to do is how to use all the information in this table and take a bunch of derivatives of, these functions composed with other functions or multiplied by other functions and so on. So that's it. Another set of derivatives to know, and that's hyperbolic functions.